this. Yes, it worked. As soon as we get the game on, then it starts to work. All right, that's. Did you guys enjoy the game?
That was good, thanks. I can now say I watched.
What's the time? It's the fourth quarter already? I like this HD. All right, enough fun. I mean, let's have even more fun. That was weird. But there was a big chunk of fuzz in there. All right, pretty simple data set. I think it's annual sales, advertising. Yeah, not a lot to get excited about. Let's see, serial correlation. So let's see if there's some serial correlation. So let's just run the simple regression. Save, and again, we run that simple regression, and the nice thing about time series data is you're almost always going to get really high R-squared, unless the data is really, really bad. You're almost always going to get really high R-squareds, as opposed to cross-sectional data like we were doing in 580, where the R-squareds tend to be a lot lower than that. But time series data, just by definition, and again, if you take any two time series, any two series, doesn't matter if they are cause and effect or not. But if we took sales, and instead of advertising, I put in, Jesus, I don't know. I'm trying to think of something completely irrelevant. The number of, no, he wasn't even born there, but I was going to say like Justin Bieber fans or something. Just pick something completely irrelevant.
It would be growing.
Yeah, if you, it would probably be dying now, but.
It's geometric.
But if you pick any two series, if they're both growing, they're going to be highly correlated by definition. So you're going to get these really high R-squareds. And we should be, it doesn't mean there's necessarily cause and effect. That's why we have that Granger causality and all that stuff, because in time series data, you just tend to get higher R-squareds. All right. So we run a regression, we get a nice big fat R-squared. We're going to save our predicted sales. We're going to see how well our predicted sales fit the data. And holy cow, we're pretty good. What we're looking for is not necessarily how good we are. We're looking for kind of, and again, this is a terrible picture, but you can almost see the pattern of residuals. We're supposed to be either over-predicting or under-predicting, and that should be occurring at random. Here we can see we're almost always under-predicting, and then we're almost always over-predicting, and over-predicting, and then, so we see that there isn't a randomness to our predictions. Now, we'll get a better view of that if we, instead of looking at these, we literally look at the residuals. That is, the difference between these two lines, and see if there's a pattern in the residuals. And that's the definition of serial correlation. Is there a pattern over time of the residuals? So to save the residuals, we use our predict command, except we just say predict. We've got to give it a name. We're going to call it error. And then you put residuals. And that's literally going to save the residuals. So it's a post-regression command. Let's see. And then we're just going to scatter those. No, let's scatter those. Let's see. Let's do that. TS. Oops. Line. Error. Now we put a Y line at 0. We know the mean's supposed to be 0.
What is happening?
Man, that was weird. Because that's not what I want. What does that say? There it is. All right, and we do see somewhat of a pattern. Falling, and come up again. So we're seeing kind of a pattern to the residuals. We also know that serial correlation is literally defined as the correlation of the errors from one period to another. So we want to look at what we call rho, the correlation coefficient. We want to look at this. Are the residuals in one period correlated with the residuals from another period? So we can actually graph that. And if the answer is yes, then we have serial correlation. All right, let's look at this command. Again, ignore all the other stuff. Basically, we can use this lag term here. So this is scattering our error against the lag error. So this is a shorthand way of constructing the lag coefficient. Stata's got a nice, easy way. We can only use that if we've already time set the data, which I did. But this is basically going to show us a scatter diagram between these two things. And remember, they're not supposed to be correlated, so we shouldn't see a positive or negative correlation. Mostly positive. And that looks like a positive correlation. So it does look like we have correlated errors. Again, these are just visuals. This is, what is this? Oh, this is already the one here. All right, so let's look at those autocorrelation coefficients and the partial autocorrelation coefficients. So, to get the autocorrelation coefficients, command is AC. And it graphs them already for you. So this is a really cool command. Boom, we're done. Remember, essentially what we're doing is graphing the correlation between the error terms. And we're looking for a pattern. Now, even though only the first one is statistically significant, we do see a pattern in the correlations. We see they're positive, then they go negative, and they pretty much stay negative except for this one here. Again, none of those in the gray area are considered statistically different from 0, except for the first one. But we do see a pattern. So again, it's another sign of serial correlation, that the errors are correlated with each other. The partial autocorrelation coefficient is essentially, if we had ran this regression, it's a graph of these coefficients here. And to get the partial autocorrelation coefficients, it's PAC instead of AC. And did I click it or not? Lag's too large, must be less than 14. So let's just do. All right. Again, this tells us the order. The first one is the only significant one, so it tells us there's first order serial correlation, which means we have that. We can put these two together. Have we done the graph combine? Graph combine is awesome because it combines graphs. Of course, combining nuclear lag. We know this should be 0. So, to combine the two graphs, run the command, you got to name it. I'm calling the first graph, graph 1, on the second graph, graph 2, and then graph combine, graph 1 and graph 2. Y common means give them the same y-axis. You can also use x common also. And this just kind of cuts and pastes them together. So you can have one graph with both of them in there. So we're going to use both of these. We might as well put them together and kind of treat them as a pair, like salt and pepper. Bam. That shows you how hip and cool I am. I'm up on the new music stuff. All right, let's do some tests. The tests are really easy. ESTAT is a post-regression command, so after we run a regression, we type ESTAT Durbin-Watson, and again, this is the test nobody really uses anymore, but we get this test statistic. Remember, 2 means there is no serial correlation. 0 means there's positive serial correlation. Here we get a Durbin-Watson statistic of 0.65. Is that statistically different from 0? We'd have to look up the Durbin-Watson statistic in some book somewhere. But since nobody uses it anymore, we don't even really care too much about it. Instead, we're going to use Durbin's alternative test, which is an improvement on the Durbin-Watson statistic. And it really gives us everything we need. So ESTAT, Durbin, alt, you got to specify some lag structure. I just use 6. And essentially what we have is a test of the null hypothesis that there is no serial correlation. And it even says it right there. H0, the null hypothesis, is there is no serial correlation. So remember, if we reject the null hypothesis, we'll conclude that there is serial correlation. So here's our chi-squared statistic. Is it statistically different from 2? These are all close to 0, so we're going to end up rejecting the null hypothesis. So it's kind of like this t-statistic, but it comes from the chi-squared distribution.
So for the homework, when we put this in our homework, because I'm sure you're going to ask us to put something like this in our homework, is this something that you can outreg somehow, or is a picture of that good enough, or?
Copy and paste
Okay,
into the
just
table.
checking. I don't know if there's another command to send
But
somewhere else.
you can outreg the you can include it in your outreg, but I'll probably have you just do this.
Okay.
Because you have to play with outreg. Outreg, you can actually pull anything that gets, because these automatically get computed when we run regressions. And that's really what we're doing, just kind of pulling them out of the memory. So yeah, copy and paste in the table, put them into Excel, clean them up, and you're good to go. The Bush-Godfrey test is again E stat B Godfrey. And again, you can see it's the same null hypothesis that there is no serial correlation. You get these chi-squared statistics, we don't need to look up the critical ones, we can just say, let's look at the p-value. And if the p-values are close to 0, then you conclude that there is, in fact, serial correlation. So what we see is that the p-values are close to 0 for, well, they're pretty close to 0 for all of them. I mean, even this would be significant at the 5% level. So that's a 3%. You round that to 3%. That's still a pretty small number. So we would still reject the null hypothesis, conclude there is, in fact, a problem with serial correlation. If there is a problem with serial correlation, we're going to use one of those transformations, those Cochrane-Orkutts, those other things. Remember that, oh, there's the Lagrange multiplier test. And that was, Lagrange multiplier test was to save the error, lag the error, and put it in the original regression, which we can do in one command here. So remember we called the error, so that's something we saved using the predict command. We can lag the error automatically with that lag operator, L dot, and that's now the lagged error. And then we check this lagged error for significance. It's got a t-stat of 4, which is high, and a p-value of 0, which is good, which tells us that our lagged error is statistically significant. It's not supposed to be, which means we have a problem with serial correlation. And again, we have this huge R squared. All right, so yeah, I think we have serial correlation. We're pretty confident in that. So we correct using some method. The method we're going to use is the Hildreth-Lew. Here's the unrestricted distributed lag. Instead of red, we're going to use praise. Praise is the Praise-Winston transformation. We don't need to do any of this, actually. We already did all this. But there's your command, there's your information criteria. Save them all, construct a table. Again, what we're looking for is a lag length, some help with lag length here. Remember, lower is better, so we're looking for these information criteria to fall, which they do, which they keep doing. So it's not really helping as much, which they haven't really. We haven't had a situation where the information criteria has helped this much. We'll play around with an unrestricted lag structure. Let's try 4. We're going to use the praise command. And you notice the output is pretty similar to the praise command. To the reg output. Except you get 2 different things. We get our estimate of rho, and rho is the correlation coefficient from our error terms. So it tells us that our error terms are correlated, correlation coefficient of about 0.6. And you get your Durbin-Watson statistic from the original model, because essentially what this does is transform the model into that nasty equation, estimates it, and then transforms it back. So the original Durbin-Watson statistic was 0.95. The new one, remember close to 0, is positive serial correlation. The transformed model it's 1.55, so we're getting closer to 2. So it's correcting for most of the surface elevation. Not exactly 2, but we're getting closer to it. All right, so that's our Praise Winston autoregressive, and again, you can see AR1 regression model. We're going to graph the lag coefficients to try to give us an idea of what model we should use. So same command, we're pulling the lag coefficients from 1, 2, 3, 4 periods, from all 4 periods. And that should say 4. All right, so 4-period unrestricted lag model. Yeah, it looks like the initial impact of advertising at time 0 is the biggest, and then it starts to diminish afterwards. Remember that the information criteria was providing no help in when to stop adding lags. So we could have added 5 periods, 6 periods, but they're bouncing all over the place. The coefficients were becoming negative, positive, negative, but they were pretty much hovering around 0. So if we were going to pick a lag structure, 4 looks as good as anything. But we can do better than that. We have this infinite distributed lag model, and we don't have to pick a lag structure. We can use the lingering effects model. So to do that, we estimate, let's get PowerPoint back in here. Game over? No? All right, to distribute. Train or the new thing? Is that thing called?
Smart.
The new thing?
The train?
Oh, is it a train? It's not a. It's not a high speed whatever.
It's high-speed train.
It's not a BART-like thing. It's a train.
Mm-hmm.
Oh, okay. Yeah, it's a train.
It's a train. So fashioned is a train.
Just an old-fashioned train. Okay. Lingering effects model. All right, so the beauty of the lingering effects model is it's, again, simplicity. We estimate, where's the estimate model? We estimate this model. Sales, this is just the intercept, and then advertising and lag sales. So the coefficient on lag sales is our lingering effects coefficient, is our carryover effect. So the coefficient on lag sales is our carryover effect, is lambda. And to graph our coefficients, we construct our beta 0 is going to be the initial impact, beta 0 plus beta 1 times lambda, beta 0 plus beta 1 times lambda plus beta 0 times lambda squared, and then lambda cubed for the 3rd period, and so on and so on and so on. So there's going to be a pattern to those coefficients. So we need to estimate this equation. Run sales on advertising, and then lagged sales. Again, we're going to use one of those transformations. And because we have lagged sales in there, we're going to use the Hildreth-Lew search procedure. The command for all of those transformations is praise. If we wanted the Cochrane-Orcutt, it would be Cochrane. For Hildreth-Lew, it's SSC, which is the search procedure. In all honesty, it's not going to make very much difference in those coefficients. We saw how little difference it made when we ran those different specifications, and it really didn't matter much. Okay. So here is our lingering effects model. Again, notice that these praise commands are iterative processes, so it actually runs multiple models and finds the value of row that best fits the model. Okay, so we get our coefficients. So the coefficient on lagged sales, and again, notice I use the lag operator, L dot. So the coefficient on lag sales is our carryover effect. And beta 0 is our coefficient of advertising, on advertising, which is 0.53. So now all we have to do is, any questions? Just go back. All right. So we use the proper procedure. So we've got sales equals alpha plus beta 0. Advertising, remember I'm using beta 0 to represent 0 lags, plus lambda lagged sales plus BT. The initial impact, beta 0. 1 period later, it's going to be that initial impact plus whatever got carried over from the initial impact, right? So this is 1 period later. 2 periods later, it's going to be beta 0 plus lambda beta 0 squared. Oops. Lambda beta 0, I said it right, plus lambda beta 0 squared. 3 periods later, it's going to be beta 0 plus lambda beta 0 plus lambda squared, beta 0 plus lambda cubed, beta 0. Oops. Beta 0. So these are our lag coefficients. Initial, 1 period, 2 periods, 3 periods. And it follows, again, basically this structure here. Each period is going to be beta I, lambda, beta 0, lambda to the I. All right, so we just need to do that. Initial effects. All right, so let's generate lag. Oh, it's already defined. Okay. So initial effect, beta 0, 1 period, so no, that's right. Yeah. So this is that period's lag effect. Then we graph them. And again, what we've done is imposed a specific shape on those. Is that right? 148. Yeah. So the coefficient is on lag sales is 0.48. So that's what sales look like. That's what the effective sales look like. Initial impact, sales raise, or increases sales by 0.5 something. Oh, I guess, yeah, 0.5 something. And then starts to decay at a rate of 0.48 per period. And again, there's no guessing or trying to figure out what the lag structure is. Let's put these two together. So here's our unstructured one where we have to figure out how many lags to continue to carry out. And here is our lingering effects model where we're saying there's a geometric decay in the effect of advertising. Big initial impact, and then over time it's just going to die out. Eventually it'll be infinitesimally small, but we can see where advertising becomes essentially unaffected, or its effects decay. We can calculate the long run effect. Remember that it was let's see, this is what? Long run effect? What's the coefficient on advertising? It's equated 0 over 1 minus lambda, right, which is the coefficient on lag sales. In the long run, sales will increase by about 103%, 104%, 1.03. How long is the long run? It's a long time. More practically speaking, we can calculate the 90% duration interval. And remember, we can do that for any interval. And remember what we're going to call P% duration interval, call it DI, is equal to the log of 1 minus P over the log of lambda. So we want the 90% duration interval, so we just plug in 0.9 for P. If we wanted the 50%, when does half of the effect of advertising die out? That'll probably be, well, that'll be sooner. So what this is saying is that